So you have to say.
That depends on.
Okay.
I can do it much faster now.
Not to take too much time away from the main thing, but there's one important thing that I wanted to do, which was so many thanks to the Newton Institute staff, without without whom this workshop could not have taken place. So in particular, they were too modest to come in. They said this is what they're for. So I wanted them to not just be names, but also have faces. But I got them to collect there, but I couldn't get them to come in. So you can just peep out and you'll get to see them. So that's what I was trying to do there, but I was unsuccessful. But let me, rather than just say the stuff, I'd like to at least say their names. Heather Brabrook, who's left now, but she did a lot of the stuff initially. But I have to say, she left a week ago, and everyone, compensated for her. It was just amazing. Sergey has more persuasive skills than I do. So. Well, I could still go through their names and then. So all of you would have, of course, met Esperanza, who helped with the housing. Sarah Fenchier did many tasks, and as well as Sue Gilbert and Christine West, the financial, Sarah Wilkinson, Stephen Williams. Then the IT support, Steve. Well, Steve's disappeared. Oh, please, well, we can give him a hand. Okay. Some hands authority to get them in. Okay, Russian. And of course, the deputy director and Ben Mestel and David Wallace, all of them played a role in this conference, so I'd really like to thank them. And in addition, also many thanks to the program committee. Thank you. So the program committee consisted of Vivek Borkar, Sergey Foss, Peter Glynn, Bruce Hayek, Frank Kelly, Pierre Kumar, Tom Kerr, Jean Mares, Philippe Robert, Jean Tsitsiklis, and Ruth Williams. And I put Francois Batelli within brackets because he was not on the program committee, but he immediately responded to my endless questions about how the last conference was organized. So I'd really like to thank all of them, and especially I bothered Frank and Ruth and many times about many other things. So thank them all for their prompt response and their help with And just two other announcements, which is, they say, the king is dead, long live the king. Just looking ahead, just wanted to advertise the ICM Satellite Conference, which is going to take place in August 2010. There's the on probability and stochastic processes. It's going to be in Bangalore, and that's the website, in case you want to. And others who... There's the Informs Applied Probability Society meeting next year, which will have topics which are quite closely related to some of the things that you've seen here that you might enjoy. So it's going to be in Sweden, July 6 to 8, 2011. And the next Stochastic Networks Conference will be in 2012, in the summer of 2012. So these are just things to look forward to. But in the more immediate future, what we look for, I think Sergey has some announcements.
Boston.
MIT.
Yeah, MIT.
Yeah, okay, I didn't know whether I should announce it. It's still in Cambridge, so if you like this one, you like that one.
I would like to bring your attention again. So each of you got a list of with information that there is a open problems issue of queuing systems. And you see, so it brings something, It's if this opportunity not only to give your own problems to colleagues or younger people, but also somehow to influence our community by posting right problems. And so for instance, I was very happy, to listen to the previous talk by Philippe Robert in particular, because I gave a talk on open problems a year ago. So I can give you. So I have good experience. So I invite you to consider seriously possibility to propose your problems, whatever your direction. So it may be just a short essay on problems you were involved. I think some of you who are more experienced may write something. But it's not just a problem. It's maybe area which maybe it's interesting to develop and so on and so on. Thank you.
And I had Sergey just reminded me of two other things, that which was the speakers that I wanted to thank, who made, and the ones to come as well as the ones so far, for making this such an excellent and the audience that was so active. I mean, I really liked it when someone said, "Turn 2 slides back." I mean, someone's really caring what you say as a speaker. That's really valuable, I think, for a speaker. So. Thanks to the audience very much for making this lively, and I don't want to take any more time away. And the people who gave the open problem sessions for their generosity, so Devavrat and Damon, as well as Sergey. Next row.
Yes, John. Thank you very much, Karita. It's a big pleasure to introduce Pablo Ferrari from Buenos Aires, who's going to talk about slow-to-start traffic models, coalescing Brownian motions, and MM1 queues.
Okay, unfortunately I had some problems with the slides, so I will do everything on the board as Sergey asked me, and I think that since what I am going to talk is not very familiar for this audience, maybe it's better to do it slow in the board. So the names, this area of slow to start models is an area that was developed essentially by Nagel and other German researchers, but mostly with simulations and with cellular automata, traffic cellular automata by Gray and Griffith, where they did a lot of simulations also, but they have some theorems. But discussing this with those people, we were looking for some model where you can show something mathematically. So we simplified the model ad nauseam. So we got the simplest possible slow-to-start model, and we showed some theorems that are already interesting, I think, and are described in the abstract, but I will try to explain them here now. Okay, so most of the talk will be about joint work with Leonardo Rolla. And this will be all the scaling limits. And with Freddy Cáceres and Eugene Pechersky. Okay, so this will be the mapping of the subcritical case you will see later to this MM1Q, and this will be the mapping to coalescing Brownian motions. Okay. Okay, let me start then with the model. So we will have particles P I of t that are in R.
Could you use the other board? That'll slide up under that one and be disappeared. No, pull that one down. Yeah, use that one.
You want this?
right on that board, and you can just
No.
Pablo, just do it the way you want.
What you want? You to start here again from zero, from scratch here?
It's okay.
Just do it.
Just do it as
Just
Okay, so it's slow to start model. I start again. And then I have cars that are points in R, and they occupy no space, only the points. And they have
They go downhill, yeah?
Pi of t is position of ith car at time t, and vi of t is speed. Okay, so I have my process is p v, that is pi of t, say pi of t, vi of t, and I is in z. Okay, and v belongs to could be 1 or 0. Okay, so I have two possible velocities, and then I have an exclusion rule. That means that cars cannot overpass. Okay, so simple, all cars start, so V0, Vi of 0 is identically 0, okay? And if P I of t, say I minus 1 of t, is strictly less than P I of t, and Vi of t is 0, okay? So if this car has space to go to the left and its speed is 0, then Vi of t jumps to 1 at rate 1. Okay, so a typical trajectory will be so I started with all the cars are at speed 0, at time 0. So if time is going up, then this car waits an exponential time and then goes at the speed 1 to the left. Then this car, maybe his waiting time is this one, then goes here, but then here it will collide with this one. So has to wait, and nothing happened until this moment. At this moment, his exponential clock starts going, and then after this exponential clock goes to the left, and so on. Okay. So this is a typical trajectory. Okay. I think this is what I wanted to say in my first thing. Well, there is a generator, but I will not write it down. Okay, it's an exercise.
Sorry, the difference between usual exclusion process is that the points are on a real line, or not?
The points are on real line, and also they have deterministic velocity. The exclusion process is a random walk to the left, the TZ, right?
Yes, but if you start from
Well, there are
integer points, and it will be zero range process, or it will be exclusion process with the velocity to the left. Is it true or not?
probably not.
Why?
No, because the behavior is totally different. The exclusion process gives rise to the Burger's equation, and this gives rise to this coalescing Brownian motion. So I don't think so. On the other hand, we here allow more than one particle per side, because here I put separate, but in fact they are in the same place.
Different, sorry.
Okay.
I understand.
When will Vi go from 1 to 0?
Sorry.
When will the velocity go from 1 to 0?
So it waits at rate 1.
From 1 to
From 1 to 0 only when it hits another car.
Oh, wait, okay. So wait, you have to jump to rate 1 when it'll go to 0 when it hits other cars.
Yeah, from 0 to 1, you go if you are free to, if your way is free. Okay, so you are in the red light and your front car left, and then now you wait because you have to look for your cell phone or whatever, exponential time, okay, to go. But then if you find a car that stopped, you stop, And then when you are free here, then you run again your exponential time. Okay? That's 4. The density of the only parameter here is the density of the initial points. Yeah.
So why does the car which is following one car when the former moves doesn't follow the one in front? So
As soon as you block, the
I don't.
exponential clock gets restarted.
They're looking at their cell phones.
Exactly.
no, I was wondering, I mean, in traffic jams, so what cars are just back to back, right? So
Yeah.
bumper to bumper. So why a car which is blocked by another one does when the former starts doesn't follow the
This one, for instance, is blocked here,
Yeah.
doesn't follow, because he's looking to the cell phone, so it waits an exponential time before. This is the low to start rule. This is the main topic here, right? That you don't go when you can go, but you wait a little bit.
Yeah, you can assume also that when he's stuck, he has his clock running, but if it tells him to
Of
go
course.
and there's a car, then he
Of course. Okay, so I will do a graphical construction of that because it will be used later. So I will call this Poisson process here y bar. This is Poisson parameter lambda. And then here I will say that this is y0, y1, y2, y3, y4. I will consider two cases. One is when it's a stationary process, so y0 doesn't need to be at the origin, and the other is the palm version where you put y0 at the origin. Okay, but then I will call this a0, 0, and the second time is a0, 1, and I will construct the whole a02, etc. Okay, a03 and a0i are exponential parameter 1. Okay, so that means the a is like a vector, a0, say, is a Poisson process of parameter 1. Okay, so the alia of this process is a Poisson process here in the line, and then a Poisson process in the semi-line attached to each one of these things. Each of these Poisson processes are independent. Yes.
It's double infinite. Initial position.
No, I don't. This one is doubly infinite. Yes. The space is doubly infinite. The time is simply infinite, and of course I will not use here all the points. For instance, here I will use the waiting time of the car at 0, the waiting time of the next car, but then all the next car will not stop here because this
stop at the original points.
nobody will stop here. So actually I will not use them, but I keep them in my
Yeah.
position. Okay.
Whenever a car is stopped, it's on the points which were initially on the line.
Yeah. So I will call traffic jams the places at time t, the places that are contained in my original Poisson process that have stopped cars at time t in that place. Okay. So for instance, say. Well, for instance, for this t, this is the only traffic jam. So this point belongs to y0. Okay, y0 is the set of y0 is contained in y original, and are the traffic jams. Okay, and then I will call ni of t is the size of traffic jam at yi. Okay. Maybe I could put a y here. Okay. So if I have for this point, in this point I have a traffic jam at this time t. Okay. How is what is the size of this traffic jam? Is 2, because I have 2 cars stopped there at that time. Okay, so I have this so I will have the process y0 n, that is a market in T, no? Market point process. And then I have also y1, that is the of T, are the positions of moving cars at T. Okay, there's, for instance, I have some colors here.
Wait, the original points.
Both of them are contained in the original process, of course. Okay, so if this is time t, the only traffic jam is this one, and all this. Okay. But I have to look at here. Okay, this is y1. Okay, and this is y0. Okay, now let me use some more notation. No, that's okay. Okay, so now I will describe the local behavior of this. So this means that I will look at the process y1 of t. So this is just a point process, that is the red point process at time t. And so this process converges in distribution to a Poisson process with parameter min of lambda and 1. Okay, lambda is bigger than 0. So I can have no more than density 1 of moving cars. Okay, I am losing, so I am losing lambda minus 1 cars at traffic jams.
Lambda again?
Well, plus, no? Yeah, lambda is the only parameter of the process, is the density of the initial cars, where the cars are initially.
This is a support of the limit, and you have marks.
Well, the marks are 1. No, because this is already moving cars have mark 1.
But for which initial condition you have this convergence?
For the only one that I
Only
talked
for
about. Yeah. The audience is invited to extend the results. Yeah. No, Poisson maybe is not crucial. Here you will see. Probably you can do it for mixing process, I guess, but it's not annoying.
Where does the one come from?
Huh?
Jump rates. Oh, yeah.
Jam race, yeah. Because you see that if you have a big traffic jam, then your cars will leave from here at rate 1. So finally you will see here a Poisson process. Okay? And essentially what happens is that you are growing traffic jams that are far away, that are going far away, because traffic jams tend to disappear. And these traffic jams are sending you cars at density 1 and are eating the remaining cars. This is what happens.
Okay, so just a question. You have initial Poisson's parameter lambda.
Yeah.
Assume lambda is bigger than 1.
Yes.
Then at time t you have two Poisson processes. Poisson process of cars which are still, yes.
Sorry, here I put.
No, some cars are in traffic jams, and some are in move. So you prove that active cars
Yes.
are the process of active cars converge to some Poisson.
Yes.
what about those who are in traffic jams? They also they form some marked Poisson process, or not?
This, yeah, I'll discuss that.
Are they asymptotically independent?
Yeah. No, they just wait. Wait for the next transparency. Okay, so on the other hand, if you look at the traffic jams, this converges to empty, okay? So there you will see no traffic jams around if you look from 0.
What, lambda less than 1?
In any case, even so you will have lambda minus 1 cars, density, lambda minus 1 cars that are stopped, but they are far away. These traffic jams are disappearing.
This is really beautiful.
Okay. Okay, now, so this is looking from origin, right? Okay, but something more interesting happens if you look from a tagged car. So now put from tagged part, tagged car. So a tagged car means that suppose that y0 is 0. This is, yeah, y0 is 0. Okay, this is fun. So suppose that you put a car at the origin and call it car 0, and the rest are Poisson. So this is just the Poisson condition to have a
By that you mean
car.
sort of y0 at time 0, 0, and then you're,
Yeah,
then you're
y0.
shifting everything to that, right?
No, wait. Now I will follow it. So
Yes, right. That's what I'm saying. But
yeah. So this is the initial position.
yeah.
Okay, now I call pi tilde j of t will be equal the position pi j of t minus pi 0 of t. Okay. So I just looking from the, so this is process pi tilde t is a process is as seen from car 0. Okay? Because I am shifting everything and looking from there. Okay. Well, here something more interesting happens because then car 0 can be in a traffic jam, so the traffic jams do not disappear from the position of car 0. So essentially, with some probability, car 0 will be in a free Poisson process traveling at speed 1, and will be the Poisson process. As seen from it, we'll see a Poisson process like y1, and with some other probability, will be stacked in a big traffic jam. So everybody around him in the limit will be stacked with him. Okay. So this I wrote it like that. So if you take pi v t convergence and distribution to with probability 1 over lambda. Here I should put lambda bigger than 1. With probability 1 over lambda, you go to Poisson 1 v1, or let's put 1 here like that. Everybody has speed 1, and with probability lambda minus 1 over lambda, you go to pi 0, that is, I don't know, delta 0, I guess. Delta 0, 0. Delta 0 means that all cars, the indexes of all cars are at the origin. But if you look at, I don't know which index will have the cars that are moving, because we'll have index minus infinity plus something, okay? If you because what happens is the following: you have this infinite traffic jam, you are here in the middle, and so your neighbors are here. This traffic car minus 1 will live at this. So you will live. Car minus 1 will live at this point. Car 0 will live at this point. Car 1 will live at this point. But this is infinity here. So you will never live. You see everything like that. So this is a convex combination of the distribution of this. So this is low, in fact. and this is the log of that. Okay? So with probability 1 over lambda, you see this. With probability 1 over lambda, you see the other thing. Okay, but then you, for instance, the velocity of each car converges in distribution to a random variable to 0 with probability 1 over lambda, and to 0 to 1, sorry, and with lambda minus 1 over lambda. Okay? And but you can show also that vi of t converges almost surely to minus 1 over lambda. And the probability, well, okay. Well, when lambda is less than 1,
And that be negative.
Placeholder, or is there a T in there, or what?
over t. Thank you. Okay, so in the subcritical, it says subcritical, you do the following: lambda less than 1, the log of pi d t converges to the log of a Poisson lambda, and all 1. Okay. This is what we did with Pechersky and Castellares. The vi of t converges to 1, and pi of t also over t converges to 1, to minus 1. In the critical case, so in this case, what happens is that just this stopping cars is just a perturbation of the system that likes to go at free traffic at distance, typical distance between cars. This is 1 over lambda. Okay? But the nice thing is that the final position of the cars is the same as the initial position. So this is like a Borque theorem for this thing, and in fact, it's a consequence of Borque theorem, this result. Okay.
You really mean minus 1 in that case?
Yeah, the cars are going to the left.
That's why you get a minus.
Yeah. This is nothing very deep. Yes. And the reason why the cars are going to the left, because normally cars should go to the right? But when I will map to the Q, you will see why it's better to go to the left. Okay, for lambda equal to 1, I have the same p tilde, v tilde. Here is tilde and tilde. Okay, p tilde, v tilde. So this is Poisson part of Poisson, no? This converges to P1. So P1 was Poisson 1 and 1. Okay, it's a distribution, so I am talking about the logs here. And but that pi vi of t doesn't converges in probability to 1, but not almost surely, because there will be infinitely many collisions between the cars in the critical regime. Okay, and this is because pi of t will be equal to pj of t infinitely often, if you allow me this. So infinitely often means that the points of the Poisson process. Okay, and then conditioned. I don't want to erase this, so I come here. Okay, the condition motion is the lambda, so the condition in motion. So I will condition that the speed is 0. So when lambda bigger or equal than 1, and I want to ask what is the probability that Bj of t is equal to 0. And okay, given that Bi of t equal to 0. Okay, here I also want that Bj of t is equal to Pi of t. Okay? So this converges to 1. So if one of the, well, this is somehow contained in the previous result. Okay? More interesting is this when lambda is less than 1. So I am conditioned to an event that goes to 0. And the probability of this event goes to 0 because all cars will get free. So if I ask which is the probability of Bj of t equal to 0, given that Bi of t equal to 0, and I will take j less than I, so to the left. Okay, this goes to the quasi-stationary distribution of the MM1Q conditioned not to be absorbed. That would be 1 minus square root of lambda square. Okay, so k lambda k minus 1 over 2. So this will be mu qs of k. Okay, so this converges already. This is the definition, and this converges. Okay, so this converges to mu qs of j minus of I minus j.
So K here is
And k is bigger than 1.
What is 1 minus root of lambda? What is written there?
Well, this is normalizing factor of this distribution.
It's coefficient.
It's k lambda k minus 1 over 2. So we put a constant here. That's
Okay.
So if you start this MM1Q with raised lambda and 1, and you condition that at time t has not been absorbed at the origin, and you start with 1, for instance, then this converges to this distribution.
This is only for the guy who's at the bottom of the clump, right? Because you
No,
have,
no.
you have
Yeah.
where you are in the clump. Huh?
No, for one side. I hope it's correct that it's to the left, yes.
No, but isn't it for the guy who is at the bottom of the clump?
Yeah.
For the others, it will be different. Because otherwise, you'll be somewhere in the quasi-station distribution.
No, I am not asking that it's in the bottom of the clamp. I am not asking here that Vi of
So you can have
Vi plus 1,
right also,
it could be.
and it doesn't matter where.
No, because it's Markovian, the motion to the left. Because the guy, because you see, this guy doesn't care about all these people. Just look in front of it and go. So it is some Markovianity here. So if you look at this,
Hurricanes, they never look in the view mirrors.
okay. Well, I don't have much time. Okay. Well, I will now find the eraser first.
They're all down.
Pablo.
Yeah.
There are
There's
two
a whole bunch down there.
There are two mob boats to use.
Yeah, but
On the left.
doesn't matter. I will start here. Can I erase here?
It's the most recent thing.
The most recent. Last come, first serve.
So now I will remember what it was y0 and n. Okay, these are the position of the stopped car, the traffic jams, and these are the size of the traffic jams. So I will rescale this and find limits. Okay. Okay. So there are three regimes. So in lambda bigger than 1, I will describe the regime for lambda bigger than 1. This is a marked Poisson process, okay? So these are coalescing Brownian motions. Coalescing Brownian motions. Okay, so at each this is Arratia. Arratia introduced these coalescing Brownian motions as a limit for the water model, the dual of the water model in the 70s, before many of you were born. Okay, so you start the Brownian motion at each side of R. So you have B, Z, S bigger or equal to 0, and Z belongs to R. Okay, so this is the object, but they are coalescing. So if you have a Brownian motion starting here and another starting here, and hit it, then this one disappears and the one that is in top follows, continues. So you can think that both of them coalesce, but the area of the top one will govern. Okay. Now, when you do coalescing Brownian motions, there are some. There is for each given t. Here, time is going like that now. For each t, there is a discrete set of points that are double points. In these points, there from this point depart two Brownian motions, and they will be different all the way up to t. Okay, and so something like that will happen. Here are all the coalescing Brownian motions are. Okay, this is another. Okay, this is double points. Okay, this will be the size associated to Z. Okay, I will call this MT of Z, and this will be called Z. Okay, so this will be ZT. So I am looking. The Z depend on T, but look at time is a subset of R at time 0. Okay, and then T of Z will be the size of the difference of the two Brownian motions that depart from that point. Okay. Okay, so now I do. It's clear what it is, this object?
So they don't actually exist, it's just a thought experiment.
They cannot be
You
simulated.
pretend that this happens.
No, I don't pretend. No, that happens.
So then what's the density of double points on the map?
What is the density?
I thought you started with just individual points on the map.
No.
There's a point. There's a
continue.
point at every real number.
Okay.
Yeah.
But which ones are the double points?
The double points are because you can do the following. You take a sequence of points converging to this point, to each real point, okay? And then you look at the position of the Brownian motion for each one of those points. Okay? And then you do it from above. If these two are different, then this is a double point.
So these just arise, you don't construct them to not intersect.
No, I didn't.
No, I mean it's just a topological fact that
yeah.
points infinitesimally close that head off in different directions. Right?
Okay, this I just was seeing. Okay, now I do the following for the.
Eventually, yes, they'll come back.
So do the following. Take L as a scaling parameter. And then I take a diffusive scaling. So I will take ALT is given lambda minus 1, that is the density of moving cars, square root of L, y0 at time LT. Okay? So I am looking at times order L, but I am rescaling the positions with the square root of L, and this is just the parameter that fits. Okay. So the result with Rolla is that this process converges. Sorry, I forgot the N. NL of t at position z will be 1 over square root of L NL of t square root of L over lambda minus 1 z. Okay, so here I multiply twice. No? Okay, this is a point that belongs to y0, okay? At time t, at time lt. Okay, so I am rescaling the points of y0 with a square root of L, and so this z will belong to this yl of t. Okay, so the result is that this process yl of t, nl of t, converges in distribution to that one, that was zt nt. Okay, so if you rescale with, you go up to time t and rescale the distance between traffic jams with the square root of L, so square root of t, and the length of the traffic jams with the square root of t, then you converge exactly to this object. So in the limit, these guys will represent the position of the traffic jams, and this will be the length of the traffic jam, or the corresponding traffic jam. Okay?
L goes to infinity.
Huh?
This is it. L goes to infinity.
L goes to infinity, yes. Sí. Okay. Okay. So, well, in lambda equal to 1,
This is true for all t simultaneously.
this as a process, yes. This is as a process, okay? This process ZTMT is Markovian. I leave it as an exercise. Okay, okay, let's take lambda equal to 1. When lambda equal to 1, I will take Wt is Brownian motion, okay? Just parameter 1. And then Bx s is Brownian motion starting at W of x. Two side. Okay, well, put say W0 equals 0. Okay, so take a two-sided Brownian motion that passes somewhere. Actually, it doesn't matter much where it passes. So this will be W, and then I will take Bx s. So this will be s bigger or equal of to s to x. Okay. And these Brownian motions are doing two things. One are reflected at W from below, and the second are coalescing. Okay? So you start at each point here, you start the Brownian motion in all this curve. And they are reflected here, but they coalesce also. Okay? It's clear what is the object.
No, you can see the continuum Brownian motion. Yes.
This is Brownian motion.
Continuum.
Yeah.
From each point.
From each point of this Brownian motion, you start a new Brownian motion with the same variance, independent in principle. The only interaction is that it reflects on the original Brownian motion that I will put it green. So my So you have this Brownian motion, then you start the Brownian motion at each side of this, reflect it here, and then they also coalesce. Okay? You will still have double points. You will have double points. So if I take, okay. Now I will take t. My time, look that my time now is going like that. So time and space now are in the same coordinate. Okay? My time is going like that. So if I will start from each of these points, and I will see if at time t after in this direction it is a double point or not. Okay? And this will be the double points here. Say, for instance, here, I don't know. Okay, and whatever. Okay? And let me see how I call these double points. The double points are x. So xt double points at t. I put quotation marks, and then nt will be the difference between y x plus, say, y plus t minus b x minus y plus t. Okay, here is the definition of this. This will be nt of x, and this will be, say, x. Is a mess here, or you can understand? Okay, so this is a double point at time t, because the Brownian motion, the up and down Brownian motion here did not meet before time t here, and then they are at distance nt of x. Okay, so this is the process, and now I don't want to erase the picture, so so the rescaling is the following: yl of t equal 1 over L y lt 0. Okay, now I divide by, so the distance now.
Pablo, could you repeat? I don't know. Maybe somebody can explain, but Günther and I, we are lost.
Okay, so look.
I couldn't answer your question.
Look.
Because that's
Okay.
my question. Yeah.
You have this Brownian motion. Okay, then I choose a point x. There is a discrete set of points x such that from here there are two Brownian motions, one that goes up and the other that
In
goes
addition to original one.
down.
So from this
Discrete
point,
set or from all points of Brownian trajectory which you have,
Yeah.
you put these two Brownian motions. How
Well, I put one at each one, but it happens that, like in the other case that you already bought, okay, there is one in a discrete subset. There are double points. So where there is a Brownian motion that goes down, so the limit from above and the limit from below are different. I call these points double points, and I call them x. xt, so x belongs to xt. If these two different paths did not meet until time t. Okay?
Can these points accumulate? They are countably many.
No, they are discrete set.
They're
No, they
discrete.
do not.
Or locally finite.
Yeah.
T converges to zero, then.
what you do if they meet before time t? What you do?
I don't count it in xt. I count it in for t smaller. So they disappear. This set is decreasing set in t.
Does it get dense when t goes to 0?
When, probably, yeah, should do.
Yeah.
Yeah.
I mean, it's got a scale.
It's discrete at all times, no? For each, it's discrete, but the density is increasing.
I mean, it's got a scaling to it,
Yeah,
right?
yeah,
So
yeah.
it actually,
Yeah.
for each time, each set looks the same up to a scaling.
Okay, now, see, I am putting 1 over L instead of 1 of the square root of L. That means that now, when lambda is equal to 1 here, no? The traffic jams, instead of being at distance square root of t, will be at distance t, at time t. But the length will be scaled as square root. Where is it? Here. So NLT here. I am using the same notation, but it's different scale. No, in fact, it's the same. But here I am using the same notation as before, but it's a different option now because I am scaling differently here. It's 1 over square root of L and LT of Ly. So, okay, and then the theorem is that it's easy to state now. This is T. Okay, so the traffic jams in the discrete case converge. The points are those, the double points, and the length is the length of the survival. The difference of the two things. Okay?
So all these Brownian motions have the same variance.
In the critical case, they are the same. Because in fact, what this green line represents is the arrival, the initial position, and these are somehow service, so the waiting times are this. If I have time, I will explain that, but actually I am a bit... Okay, so, well, I will lambda less than 1, I will skip a bit, okay? This has to do with quasi-stationary distribution, but essentially goes to I will do a picture. So there is this e to the minus 1 minus square root of lambda t will be the, so this will be the typical distance between two traffic jams. Okay, and the traffic jams will have mu qs in the limit. Okay, you have to rescale exponential. So the traffic jams are really very, very far away. But if you find one, it will have that distribution I described it before. Okay, let's do it fast because if not, I will not do what I want. Okay, now okay, in fact, all of this is very easy if you find the right way of doing things, and you will be surprised that there is a bunch of it. Okay, so the point is that you have to find the right representation for this picture. I will try to do it here. Okay, so the first thing is to put, so I am entering here in the tools, okay? The tool of proof is a picture that is equivalent to this, but is most similar to those Brownian motions. Okay, so what you do is the following. First, put the green line. So the Poisson process here of arrivals will be a counting process. In fact, these two pictures just put this as okay. So you have this counting process. Okay? This is the green line, and then will, in some point, will be that Brownian motion there. Okay, now you take, for instance, this is particle 0. So the distance between the particles, okay, so in some sense is this, no? The distance, the initial distance between the particles. But now at time 0, I will attach a Poisson process that will be this A0, A1, etc. I will write it here. So this should be A0, 0, and this A0, 1, and then like that. Okay. Okay. And then from here I get this long thing, I guess like that. Yeah. And then another one that is this one. So it's 1, 2. I think goes like that. Because, well, this I could make this. Okay, so I do that, then I get this thing. Okay, and then this guy is this. And no, here I mixed it up everything. So no. I'm cooking the picture. Whatever, this I don't care about this. Okay, but okay, so the Poisson processes here that you have the Poisson process, the horizontal Poisson processes, and the vertical Poisson processes now are all represented in the same direction. Time and space are mixed up here. Okay, but you can, from this picture, you can recover the previous picture, because what this picture is telling you is that this particle 0 has to wait this time, and then here you have the length of the traffic jam at particle 0. Okay, that is 1 during all this time, and then at this point is 2. Is it okay? No, no, I am cheating you badly. No, what happened is this is short thing, and this is like that. So this is this, okay? And this is A00, and this is A01. You do it then at home, and you will see that it's correct. Okay, but anyway, now you see here the picture that we found in Brownian motion, because these are Poisson processes that are coalescing, because when you meet a previous Poisson process, you continue with it, because you remember we used only these 2 points of this Poisson process, then this disappears. Once that you meet, the traffic jump of 0 disappears, and this happens in this time. Okay, so this distance here is the size of traffic jam at 0. Okay. Okay. Now you have a small lemma saying that this map is inversible, and then you can look, for instance, at what happens with one particle. What happens with this particle 0, for instance. Particle 0 is stuck at 0 all this time here, and then it jumps. That means that at this time, it leaves its original time, but at this time, it is at this position. Okay, so this line here represents the time that the particle was moving from this to this traffic jam. Okay, so you can follow it, and then you can prove all those large numbers, everything, because everything is function of these Poisson processes that are increasing on one side. Okay, now let me say a word only about the rescaling. The problem the problem, the advantage is that when lambda is bigger than 1, this green line has a slope square root of L when you rescale everything. So, and we are looking at things that are at this distance. No? If we want to see the traffic jam at 0, will be at this distance. But when L goes to infinity, this collapses to a vertical line, and then you get the picture of the Brownian motion. Okay? So if you do a Brownian rescaling of this Poisson process, the green line rescales differently because it has a different density. So it collapses to a vertical line, and the other, and then you get exactly that picture. In the critical case, the green line has the same density as the other lines, and then you get the other picture I was describing there. Okay. 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 So this was the proof. But I promised James that we will send this to this special issue, so you will be ready. So let me just I want just to say that in the subcritical case, the final moving points, the final points of the final relative positions of the cars, because every car will get eventually speed 1 and will not be stopped by any traffic jam. Okay, so you can think about the relative positions of the cars. These positions are going away, but you can look at the relative positions. Okay, so what you can do, what we do is the following. Let's see. We map this. Suppose that there are no cars here. I have how long?
About 2 minutes.
Okay, no cars here, and then I can construct the cycles, say. Okay, so I will say that this is a cycle because the next car that because there are no cars here, so this car will get free at this point, and this other car will get free at this other point. Okay, and then this car is after those, so will not interact with these two. Okay, okay. Now here are two variables. This will be sigma 0, and this will be sigma 1. You can do this picture as complicated as you want, but the sigmas are the ultimate waiting time. So from this point on, this car 1 will be free and will wait for an exponential time of sigma 1. Okay, and these sigma are independent. Even if you do some more complicated things, this ultimate time of waiting time will be independent random variables. Okay, now you map this to a Q by as follows. Let me use another color. I will use the Y0 is the arrival time. The sigma 0 is the service time of the client 0. So this client do like that until this moment when another client arrives, and it arrives with a load sigma 1, and then you have this picture that must be familiar for you. Okay, so it's just the loading process of M1Q. Okay, so if the expected value of the sigma, so the expected value, my sigmas are independent exponential of parameter 1, and my process here is a Poisson process parameter lambda less than 1. Okay, and these positions, when you project this, these are the ultimate positions of the particle when they are free, projected to the original point. Okay, okay, but now this is a cycle of MM1Q. So you put one cycle after the other, stationarize. Okay, and then you get a stationary MM1Q that you map to a stationary traffic process, and so and this is of course the departure process of your Q that will be the same as the positions of the final positions of your cars. Okay, I guess I finished here. Okay.
coalescence, you have the regeneration. So after the first waiting time exponential, there is positive chance that you will never stop in the future.
When lambda is less than 1,
infinity.
yes.
So you get regeneration. So it's to some extent.
Yeah.
You know it, okay?
Yeah.
I got it finally.
Okay, in that case, thank you very much.
Okay, thank you.